Hi everyone, I'm Lucy, and I will be sharing our paper titled Persistent Nature, a generative model of unbounded 3D worlds. In the traditional graphics pipeline, creating landscapes is a very manual process, illustrated by these clips from 40-minute-long YouTube videos. So here we explore creating worlds automatically, learn from 2D photos without 3D ground truth. Our desired properties for these worlds are spatial consistency, so the pixels move in a way that respect 3D geometry and camera motions. Unbounded generation, so we can move the camera arbitrarily far. And persistence, so that we can return to previously seen content without the scene changing. As the camera traverses this figure 8 pattern, I'll copy the first frame of the video here. So when the camera returns back to the starting position, you'll see it approach the same scenery that we saw at the start of the video. Our model is based on 2 threads of prior work. One is autoregressive prediction, which can support unbounded camera movement, but there is no persistent representation, so the scene looks different when moving backwards. On the other hand, recent 3D generators have a persistent global feature representation, but they tend to operate on domains with limited camera movement, such as forward-facing, object-centric, or indoor scenes by training on a volume of limited extent. Our model aims to combine the strengths of these 2 previous approaches, and we show examples of our model output in the videos below. We use a global feature representation for scene persistence, but the features can be extended at inference time to create a large-scale feature map. Sampled landscapes from our model include mountains, lakes, and snowy scenes. Towards our goal of generating 3D worlds, we build our model in 3 stages. First, we learn a generator for 3D terrain from 2D photos. Next, we need to extend this terrain to support unbounded camera motion. And last, we separately model content that is far away, such as the sky. Let's start by learning 3D terrain. We'll use a generator network to create a 2D layout representation. This is a 2D grid of features on the ground plane, but these features contain the information that represents a full 3D world of content. To decode these 2D features into 3D features, we'll place a camera on this feature plane and shoot rays across the feature grid. We'll sample points on these rays and project each point onto the 2D feature plane. Then we'll use a layout decoder network that takes in the layout feature and the height above the grid at each point and converts it into an occupancy value and a 3D feature. By volume rendering the 3D features sampled along camera rays, we can obtain our initial image and some associated outputs such as a sky mask, projected 3D features, depth, and a projected world space noise pattern. The learning of this is supervised with a discriminator objective, so it doesn't need any sort of reconstruction loss or 3D ground truth, which is hard to obtain at a scene level. And because the rendering operation is expensive, we'll first render at a lower initial resolution, and then use a refinement network to improve the texture of the result. This is also supervised with a discriminator loss, and so far we've skipped over the sky, which is currently left as empty space. To train, we'll use 2D unposed and single-view landscape photos from LHQ. We extract disparity and sky segmentation from the DPT model. We train the terrain generator using the segmented images, which encourages the model to put 0 volume density in the sky. Next is layout extension, allowing us to move the cameras beyond the training distribution at inference time. To do this, we sample a grid of latent codes, each of which independently generates a feature map. We blend features from adjacent latent codes using a method called SOAT in 2 dimensions. This operates on a 2x2 subgrid and applies the same latent code over the subgrid to get modified features, which are then multiplied by interpolation weights. This is repeated for each of the 4 corner latent codes and each layer of the generator. The result is a blended feature like this, with arbitrary spatial size depending on how many times we apply the stitching procedure. Now let's look at how to handle distant content. We train a Skydome generator that takes in a frame of the terrain image and encodes it using a pre-trained image encoder. These features are decoded using a sky generator, which produces output representing the sky and faraway mountains. The generator is trained so that overlaying the terrain on the sky produces a realistic image. But it is also coordinate conditioned, so the coordinates can be unraveled to obtain a 360-degree result. To compare with prior approaches, here is a visual comparison with autoregressive models. These models are good at moving forward by repeatedly applying a prediction model, but they generate different content when moving backward. Quantitatively, our model performs better under long-range camera motions, and while a bit less smooth than Infinite Nature 0, it is fully cycle consistent. Next, here is a visual comparison of 3D generators, which operate on bounded domains, so there is a limited distance the camera can move before the scene or geometry starts to degrade. Here, our model also better supports camera positions outside of the training distribution, with consistency close to that of EG3D due to a difference in upsampling. One trick we found helpful was that spatial noise helps to improve texture, but we need 3D consistent noise. Without noise, the model tends to generate grid-like textures with worse visual quality. The 2D noise from StyleGAN helps to improve texture, but causes a sticking pattern. We use projected world space noise to improve textures while minimizing the sticking effect. Our model also works interactively to navigate through synthetic worlds controlled by our keyboard arrow keys. To summarize, we tackle the problem of generating persistent and unbounded 3D landscapes. We generate the terrain from extendable layout features, which are lifted to 3D, decoded, and volume rendered. And we use a panoramic skydome for distant content. Our setup doesn't require any special dataset collection and is learned from landscape images without 3D ground truth. Thanks for watching, and please check out our paper and project page for more information.